Rational expressions look at the fractions that have variables in their denominators and often numerators too. For example, x squared over x plus 3 is a rational expression. Just as we can add, subtract, multiply, divide, we can perform the four operations on rational expressions. Rational expressions also represent the division of one polynomial expression by another. Last fraction represents a division of 2 squared by x plus 3, or for which we can find a quotient and a remainder. Video.
When we first started learning about fractions or rational numbers, we learned about the idea of putting things in lowest terms. So if we saw something like 3, 6, we knew that 3 and 6 share a common factor. We know that the numerator, well, 3 is just 3, but that 6 could be written as 2 times 3. And since they share a common factor, the 3 in this case, we could divide the numerator by 3 and the denominator by 3, or we could say that this is just 3 over 3, and they would cancel out. And in lowest terms, this fraction would be 1/2. Or, just to kind of hit the point home, if we had 8 over 24. Once again, we know that this is the same thing as 8 over 3 times 8, or this is the same thing as 1 over 3 times 8 over 8. The 8's cancel out, and we get this in lowest terms as 1/3. The same exact idea applies to rational expressions. These are rational numbers. Rational expressions are essentially the same thing, but instead of the numerator being an actual number and the denominator being an actual number, they're expressions involving variables. So let me show you what I'm talking about. Let's say that I had 9x plus 3 over 12x plus 4. Now this numerator up here, we can factor it. We can factor out a 3. This is equal to 3 times 3x plus 1. That's what our numerator is equal to. And our denominator, we can factor out a 4. This is the same thing as 4 times 3x. 12 divided by 4 is 3. 12x over 4 is 3x. Plus 4 divided by 4 is 1. So here, just like there, the numerator and the denominator have a common factor. In this case, it's 3x plus 1. In this case, it's a rational, it's a variable expression. It's not an actual number. We can do the exact same thing. They cancel out. So if we were to write this rational expression in lowest terms, we can say that this is equal to 3 over 4. And that's equal to 3 over 4. Let's do another one. Let's say that we had x squared is equal to, so let's say we had x squared minus 9 over 5x plus 15 over 5x plus 15. So what is this going to be equal to? So the numerator, we can factor as a difference of squares. We have x plus 3 times x minus 3. And in the denominator, we can factor 5 out. This is 5 times x plus 3. So once again, a common factor in the numerator and the denominator, we can cancel them out. But we touched on this a couple of videos ago. We have to be very careful. We can't cancel them out. We can't say that this is going to be equal to x minus 3 over 5. But we have to exclude the values of x that would have made this denominator equal to 0. That would have made the entire expression undefined. So we could write this as being equal to x minus 3 over 5. But x cannot be equal to -3. -3 would make this 0, or it would make this whole thing 0. So this and this whole thing are equivalent. This is not equivalent to this right here, because this is defined at x is equal to -3, while this isn't defined at x is equal to -3. So to make them the same, I also have to add the extra condition that x cannot equal -3. And so likewise over here, if this was a function, if this was, let's say we wrote y is equal to 9x plus 3 over 12x plus 4, we want to graph it. When we simplify, the temptation is, oh, well, we factored out a 3x plus 1 in the numerator and the denominator, they cancel out. The temptation is, say, well, this is the same graph as y is equal to the constant 3/4. This is just a horizontal line, and y is equal to 3/4. But we have to add one condition. We have to exclude the x values that would have made this thing right here equal to 0. And that would have been 0 if x is equal to -1/3. If x is equal to -1/3, this or this denominator would be equal to 0. So even over here, we'd have to say x cannot be equal to -1/3. That condition is what really makes that equal to that. That x cannot be equal to -1/3. Let's do a couple more of these, and I'll do these in pink. Let's say that I had x squared plus 6x plus 8 over x squared plus 4x. Actually, even better. Let me do this a little bit. X squared plus 6x plus 5 over x squared minus x minus 2. So once again, we want to factor the numerator and the denominator, just like we did with traditional numbers when we first learned about fractions in lowest terms. So if we factor the numerator, what two numbers, when I multiply them equal 5, and I add them equal 6, well, the numbers that pop in my head are 5 and 1. So the numerator is x plus 5 times x minus 1. And then our denominator, two numbers, multiply -2, add them -1. -2 and +1 pop out of my head. Negative, this is a +1, right? X plus 5 times x plus 1, right? 1 times 5 is 5. 5x plus 1x is 6x. So here we have negative, we have a positive 1 and a negative 2. So x minus 2 times x plus 1 times x plus 1. So we have a common factor in the numerator and the denominator. These cancel out. So you could say that this is equal to x plus 5 over x minus 2. But for them to really be equal, we have to add the condition. We have to add the condition that x cannot be equal to negative 1. We cannot, because if x is equal to negative 1, this is undefined. We have to add that condition because this by itself is defined at x equals negative 1. You can put negative 1 here and you're going to get a number. But this is not defined at x equals negative 1. So you have to add the condition for this to truly be equal to that.
Okay. Oh great, Twitch isn't working. Okay. If you just like fractions but factoring, you're probably familiar with fractions like 5 or 10. You factor out to 5 from both new, get the 1/2. You factor expressions, we're going to scan the factors that appear in both the numerator and denominator. These factors are polynomials. Expression x plus 1 over 2x plus 2 by factoring out the x plus 1. Both numerator and denominator, and canceling them by this 1/2. Okay, let's see, get rid of 2 over, okay, get rid of that, okay, yeah. On the SAT, the numerators and denominators of rational expressions can also be quadratic expressions and higher order polynomials, so the ability to factor these expressions fluently is key to success. Oh my god. Okay. The rational expression of 2x squared minus 5x plus 6 over x squared plus x minus 6. Let me see. X minus 6. X plus 1. What am I supposed to do about this? Okay.
I can't tell you how to see me. Just a cage of bones. There's nothing inside. Will it always be burning down the walls? Is there a way for me to break? I'm a sharpshooter at Paul's masquerade. I'm in both face and mind, a free for you to draw. I'm a sharpshooter, have no face to show. Please don't take off my mask, night is high.
So up here we are multiplying two rational expressions, and here we're dividing one rational expression by another one. Now what I encourage you to do is pause these videos and think about what these become when you multiply them out, and maybe you simplify it a little bit. And I also want you to think about what constraints do you have to put on the x values in order for your resulting expression to be algebraically equivalent to your original expression. So let's work it out together just so you realize what I'm talking about. So this is going to be, in our numerator, we are going to get 6x to the third power times 2. In our denominator, we're going to have 5 times 3x. And we can see both the numerator and the denominator are divisible by x. So let's divide the denominator by x, we get 1 there. Let's divide x to the third by x, we get x squared. And we can also see that both the numerator and the denominator are divisible by 3. So divide 6 by 3, you get 2. Divide 3 by 3, you get 1. And we are left with 2x squared times 2, which is going to be 4x squared over 5 times 1 times 1 over 5. We could also write that as 4/5 x squared. Now, if someone just presented you on the street with the expression 4/5 x squared and say, for what x is this defined? Select any x here. X could be 0, because 0 squared is 0, and 4/5 is just 0, so it doesn't seem to be defined as 0. And that is true. But if someone says, how do I have to constrain this in order for it to be algebraically equivalent to this first expression? Well, then you'd have to say, well, this first expression is not defined for all x. For example, if x were equal to 0, then you would be dividing by 0 right over here, which would make this undefined. So you could explicitly call out x cannot be equal to 0. And so if you want this one to be algebraically equivalent, you would have to make that same condition. X cannot be equal to 0. Another way to think about it, if you had a function defined this way, if you said f of x is equal to 6x to the third over 5 times 2 over 3x, and if someone said, well, what is f of 0? You would say f of 0 is undefined. Why is that? Because you put x equals 0 there, you get 2 divided by 0, x undefined. But if you said, okay, well, can I simplify this a little bit to get the exact same function? Well, we're saying you can say f of x is equal to 4/5 times x squared. But if you just left it at that, you get f of 0 is equal to 0. So now it would be defined as 0. But then this would make it a different function. These are two different functions the way they're written right over here. Instead, to make it clear that this is equivalent to that one, you would have to say x cannot be equal to 0. Now these functions are equivalent. Now if you said f of 0, you'd say, all right, x cannot be equal to 0.
I just realized
This would be the case if x is anything other than 0. It's not defined for 0. So you say f of 0 is undefined. So now these two functions are equivalent, or these two expressions are algebraically equivalent. So thinking about that, let's tackle this division situation. So immediately when you look at this, you say, well, what are constraints here? Well, x cannot be equal to 0, because if x was 0, this 5x to the fourth over 4 would be 0, and you'd be dividing by 0. So we can explicitly call out that x cannot be equal to 0. And so if x cannot be equal to 0 in the original expression, if the result, whatever we get from the resulting expression, in order for it to be algebraically equivalent, we have to give this same constraint. So let's multiply this. So let's do the division. So this is going to be the same thing as 2x to the fourth power over 7 times the reciprocal times the reciprocal. This is going to be 4 over 5x to the fourth, which is going to be equal to the numerator. We're going to have 8x to the fourth. 8x to the fourth, 4 times 2x to the fourth, over 7 times 5 times x to the fourth is 35x to the fourth. And now there's something we can do a little bit of simplification here, but the numerator and the denominator are divisible by x to the fourth. So let's divide by x to the fourth, and we get 8 over 35. So once again, you just look at 8 35. Well, this is going to be defined for any x. X isn't even involved in the expression. But if we want this to be algebraically equivalent to this first expression, then we have to make the same constraint. X cannot be equal to 0. And to see, this even seems a little bit more nonsensical. To say x cannot be equal to 0 for an expression that does not even involve x. But one way to think about it is imagine a function that was defined as g of x is equal to all of this business here. Well, g of 0 would be undefined. But if you said g of x is equal to 8/35, well, now g of 0 would be defined as 8/35, which would make it a different function. So to make them algebraically equivalent, you could say g of x is equal to 8/35 as long as x does not equal 0. You can say it's undefined if you want. Undefined for x equals 0. But you don't even have to include that second row. That will literally just be undefined. But now, this expression, this algebraic expression, is equivalent to our original one, even though it's 4 times 2x to the 4 over 7 times 5 times x to the 4 is 35x to the 4. And now there's something we can do a little bit of simplification here, but the numerator and the denominator are divisible by x to the 4. So let's divide by x to the 4, and we get 8/35. So once again, you just look at 8/35. Well, this is going to be defined.
Okay, same rules for multiplying dividing fractions apply to multiplying dividing rational expressions. Yeah. Limited expressions. Recall the dividing by a fraction is equivalent to multiply that fraction's reciprocal. However, to avoid lengthy polynomial operations, it's recommended that you factor and cancel any cancelable factors before you write the final expression. To multiply two rational expressions, factor any factor numerators 9, canceling identical factors, appear both numerators and denominators. Multiply the remaining numerators and multiply the remaining denominators. Dividing two rational expressions to multiplying. Just remember that dividing an expression is equivalent to multiplying by the reciprocal of the same expression. Product of this. Get rid of this, get rid of this, and cross those out, and then you just get X. Yeah. How are we doing, chat? Okay, if that and that, what is that? Okay, so 1, 1. Okay, so X plus 1. Remove this. This. Okay, what is that like? Triple X plus 2. WX. And then the 1. That does not look right. Wait. No, that's not right. Okay, so good. No. Hold on. That's 1, 2, okay. I thought we go from remove X. How do we remove? How do we cancel on X? I don't think we can. Yeah, I got it right. Oh, they already simplified it. Okay. Well, what's one of those? Okay, there's denominators. So it can be factored. Okay. Okay, 2 and 1. Yep. X plus 1. X plus 1. What's the bottom one? Three X plus X plus 1. I don't see it. Huh? Okay. X plus X squared. Okay, like, yeah, that. Oh, okay, you gotta move it from. It is cross multiply. Yeah, wait a second, but how is that wrong then? Both in the yeah, you can multiply the two expressions. Okay, but how is this wrong then? Like, you cross out that, you cross out that. How was this wrong? That was... Which of the following can... Oh my god. That's...
Pause the video and try to add these two rational expressions. Okay, assuming you've had a go at it, now we can do this together. So the first thing that you might have hit when you tried to do it is you realize that they have different denominators. And it's hard to add fractions when they have different denominators. You need to rewrite them so that you have a common denominator. And the easiest way to get a common denominator is you can just multiply the two denominators, especially in a case like this where they don't seem to share any factors. Both of these are about as factors as you can get, and they don't share any common. So let's let's set up a common denominator. So this is going to be equal to something. It's going to be equal to something over our common denominator. Let's make it 2x. Make it 2x minus 3 times 3x plus 1 times 3x plus 1, and then plus something else over 2x minus 3 times 3x plus 1 times 3x plus 1. And so to go from just a 2x minus 3 here in the denominator to a 2x3 times 3x plus 1, we multiply the denominator by 3x plus 1. So if we do that to the denominator, we don't want to change the value of the rational expression. We'd also have to do that to the numerator. So the original numerator was 5x. So the original numerator was 5x. And now we're going to multiply it by the 3x plus 1 times 3x plus 1. Notice I didn't change the value of this expression. I multiplied it by 3x plus 1 over 3x plus 1, which is 1 as long as 3x plus 1 does not equal 0. So let's do the same thing over here. Over here I have a denominator of 3x plus 1. I multiplied it by 2x minus 3. So I would take my numerator, which is negative 4x squared, and I would also multiply it by 2x minus 3. 2x minus 3. Maybe parentheses around this so it doesn't look like I'm subtracting 4x squared. And so then I can rewrite all of this business as being equal to, well, in the numerator I'm going to have 5x times 3x, which is 15x squared, 5x times 1, which is plus 5x, and then over here, just read, see I can do 4x times 2x, negative 4x times 2x, which would be negative 8x squared, and then negative 4x times negative 3, which is plus 12x squared. Did I do that right? Negative, oh, let me be very careful. Negative 4, my spider sense can tell that I did something shady. In fact, if you want to pause the video, you can see, try to figure out what I just did. It's wrong. The negative 4x squared times 2x is negative 8x to the third power. Negative 8x to the third power. And then negative 4x squared plus times negative 3 is 12x squared. And then our entire denominator, we have a common denominator now, so is 2x minus 3. 2x minus 3 times 3x plus 1. Times 3x plus 1. Now let's see, how can we simplify this? This is all going to be equal to rational expression. And so let's see, we can look at, our highest degree term here is the negative 8x third, negative 8x to the third power. And then we have a 15x squared. We also have a 12x squared. We can add those two together to get a 27x squared. So we've already taken care of this. Those two, and we're just left with a 5x. So plus 5x, and then all of that is over 2x minus 3 times 3x plus 1. And we are all done. Doesn't seem like there's any easy way to simplify this further. You can factor out an x on the numerator, but that's not going to cancel out with it. It looks like we are all done.
subtracting rational expressions. Yeah, adding rational expressions, but unlike denominators. Okay. Remember, you can only add subtract numerators from rational expression to the common denominator. In most cases, the easiest way to find common denominators is to multiply the two unlike denominators, b and b. Add subtract rational expressions, find a common denominator for two expressions. In most cases, the probability of the two denominators work. Rewrite the equivalent form for each rational expression using the common denominator, and to subtract the numerators of the expression while retaining the common denominator from my terms. Factor and or cancel as needed. Okay, so factoring happens last. The sum of that, let's see. They got the same denominator. So x squared plus that can be, because of that, it can be referred to as x plus 1 and x plus 3, and then that cancels out from the bottom, so this cancels out, and it should become x plus 1. Yes. Difference in this. So that becomes 2x times x plus 1 minus 3 times x plus 3. And then both of those cancel out. Both of these cancel out, I should. Right to come in as a denominator, so I'll obtain the common denominator for my terms, and write the result. Okay, so it should be like 2x minus 3. Okay, so 2x squared plus 2x squared plus 2 minus 3x plus 3x minus 9. then there's like x for 3. And that seems to be okay. The last wants to find the sum of 3 over x and x over 2x minus 3 in order to add in two rational expressions. Let's find the common denominator by multiplying the two denominators. Like she needs to rewrite the use the common denominator. The first term can be written as that. The second term can be rewritten as, what is it? X squared over x squared and x squared and then 2x squared minus 3x. Yeah. How do I rewrite a rational expression as a quotient and a remainder?
We're told divide the polynomials. The form of your answer should either be just a clean polynomial or some polynomial plus some constant over x plus 2 where p of x is a polynomial and k is an integer. Fair enough. And if we were doing this on Khan Academy, this is a screenshot from Khan Academy, we would have to type this in, but we're just going to do it by hand. And like always, pause this video and try to do it on your own before we work through it together. Alright, now let's work through it together, and what we're trying to do is divide x plus 2 into 3x to the third power plus 4x squared minus 3x plus 7. And so, like always, we focus on the highest degree terms first. X goes into 3x to the third power how many times? Well, 3x squared times. We'd want to put that in the second degree column, 3x squared. 3x squared times 2 is 6x squared. 3x squared times x is 3x to the third power. There's something very meditative about it. Anyway, we'd want to subtract what we just wrote from what we have up here. So let's subtract. And these characters cancel out. And then 4x squared minus 6x squared is negative 2x squared. Bring down that negative 3x. And now we would want to say, hey, how many times does x go into negative 2x squared? Well, it would go
Okay, what happened?
Anyway, we'd want to
Where did you get
3x to the third power how many times? 3x squared times. We'd want to put that in the second degree column, 3x squared. 3x squared times 2 is 6x squared. 3x squared times x. We want to put that in the second degree column, 3x squared. 3x squared times 2 is 6x squared. 3x squared times x is 3x to the third power.
Yeah, why did you multiply that?
Something very meditative about it. Anyway, we'd want to subtract what we just wrote from what we have up here. And these characters cancel out. And then 4x squared minus 6x squared is negative 2x squared. Bring down that negative 3x. And now we would want to say, hey, how many times does x go into negative 2x squared? Well, it would go negative 2x times. Put that in our first degree column. Negative 2x times 2 is negative 4x. Negative 2x times x is negative 2x squared. Now we want to subtract what we have here in orange from what we have up here in teal. So we either put a negative x squared, bring down that negative 3x, and now we would want to say, hey, how many times does x go into negative 2x squared? Well, it would go negative 2x times. We put that in our first degree column. Negative 2x times 2 is negative 4x. Negative 2x times x is negative 2x squared. Now we want to subtract what we have here in orange from what we have up here in teal. So we either put a negative around the whole thing, or we distribute that negative and that becomes a positive, that becomes a positive. And so this is equal to, the x squared terms cancel out. Negative 3x plus 4x is just going to be a straight up x. Bring down that 7, x plus 7. How many times does x go into x? Well, one time. Use a new color here. So how many times does x go into x? It goes one time. Put that in the constant column. 1 times 2 is 2. 1 times x is x. We want to subtract these characters. And we're left with 7 minus 2 is 5. And so we can rewrite this whole thing as 3x squared minus 2x plus 1 plus the remainder 5 over x plus 2. One way to think about it is, hey, I have this remainder. I'd have to keep dividing it by x plus 2 if I really want to figure out exactly what this is. Now, if I wanted these expressions to be completely identical, I would put a condition on the domain that x cannot be equal to negative 2, because if x was equal to negative 2, we'd be dividing by 0 here. But for the purposes of this exercise, you just have to input this part right over here. You have to type it in, which I guess isn't the easiest thing to do in the world.
Okay, I guess I understand it.
Alright, in the next video.
I guess I understand it. We can represent the rational expression as x equal to over bx, or a and b are polynomial expressions in terms of x. For example, ax equals to x squared plus 2x plus 4, and bx is equal to x plus 3, and that is 2x, so x squared plus 2x plus 4 over x 3. When dividing a and b, we can find the question polynomial q and the remainder r, such that ax divided by bx is equal to qx plus rx plus bx. Where the degree of r is just the degree of b, since b is usually the first degree polynomial, ax plus b, and the SAT, r is usually a constant. When dividing two polynomials using line division, we focus on the highest degree term in the numerator and denominator first. Example for that, highest degree is 2x, x squared, and the highest degree denominator is x. So the first question is, what is 2 squared divided by x, which is x. So we write x in the first term in question, from the first term of quotient q, and then the product of x. And a divisor of x plus 3, then subtract the product for a, this one leads to x squared, and the dividend. Okay. Okay. Next you do what's left of the dividend, minus x plus 4, we ask what is x minus negative x divided by x, which is negative 1, to the negative 1 in the second term of the quotient, and the product of negative 1 and the divided by that, negative x plus 4. Okay, I kind of understand it. I think I understand it. Therefore, is that the final? Yeah, that is the final part. Now let's try to define the quotient and its group numerator, which requires us to put the numerator of a rational expression into a polynomial divisible by the denominator and remainder. You don't need to know how to group the numerator, but I mean, save you time on the test. Grouping. Shut up, come.
watching these videos, you know that we have a lot of scenarios where people seem to be walking up to us on the street and asking us to do math problems. And I guess this will be no different. So let's say someone walks up to you on the street and says, quick, you, x squared plus 5x plus 8 over x plus 2. What can this be simplified to? Or what is x squared plus 5x plus 8 divided by x plus 2? Pause this video and see if you can work through that. So there's two ways that we can approach this. We can try to factor our numerator and see if we have a common factor there. Or we can try to use algebraic long division. So let's first try to factor this numerator. And we would ideally want x plus 2 to be one of the factors. So let's see, what two numbers can add up to 5, and when I multiply them I get to 8. And ideally 2 is one of them, so I could think of 2 and 3, but 2 times 3 is going to be equal to 6, not 8. And I can't think of anything else. But that still gives us some progress. Because what if we did say, alright, let's rewrite part of it. What if we were to write x squared plus 5x, and we want to write a plus 6 because that actually would be divisible by x plus 2. So I'm going to write a plus 6, but of course we have an 8 here, so then we're going to have an extra 2 right over there. And then all of that is divisible by x plus 2. And now I can rewrite this part up here in orange. That is x plus 2 times x plus 3. So let me write it here. X plus 2 times x plus 3. I still have that plus 2 sitting out there in the numerator. Plus 2. And then all of that over x plus 2. Or I could write this as being over x plus 2. And this being over x plus 2. All I did is I said, hey, if I have something plus something else over x plus 2, that could be the first something over x plus 2 plus the second something over x plus 2. And then here, we can say, hey, look, this first part, as long as x does not equal negative 2, because then we would be changing the domain, then these two would cancel out. Well, you can say, hey, I'm just dividing the numerator and the denominator by x plus 2. And so this would be equal to x plus 3 plus, I don't necessarily have the parentheses there, plus 2 over x plus 2. And I would have to constrain the domain. So this is for x does not equal negative 2. So in this situation, we had a remainder. And people will refer to the 2 as the remainder. We divide as far as we can, but we still have, it still remains to be done to divide the 2 by x plus 2. And so we would refer to the 2 as the remainder. Now that wasn't too difficult, but it also wasn't too straightforward. And we'll see that this is a situation where the algebraic long division is actually a little bit more straightforward. So let's try that out. And once again, pause this video and see if you can figure out what this is through algebraic long division. So we're trying to take x plus 2 and divide it into x squared plus 5x plus 8. Look at the highest degree terms, the x and the x squared. X goes into x squared x times. Put it in the first degree column. X times 2 is 2x. X times x is x squared. Subtract these from x squared plus 5x, and we get 5x minus 2x is 3x. X squared minus x squared, that's just 0. Bring down that 8. Look at the highest degree term, and we get x goes into 3x 3 times. Put that in the constant column, or the 0th degree column. So plus 3. 3 times 2 is 6. 3 times x is 3x. Subtract these. And we're left with, scroll down a little bit, you're left with, those cancel out, and you're left with 8 minus 6, which is indeed equal to 2. And we could say, hey, we don't really know how to divide x plus 2 into 2 for an arbitrary x. So we will say, hey, this is going to be equal to x plus 3 with a remainder of 2. Now once again, if you wanted to rewrite that original expression and you wanted to be completely the same, including the domain, you would have to constrain the domain just like that.
Okay, I'm sorry. What did I say?
Let's try that out. First, bring down.
I think factoring is still easier for me to comprehend than
we get x
this.
equals to 3x 3 times. Put that in the
Because I never learned how to
0
do long division on
plus 3.
like
3
that.
times 2 is 6. 3 times left with 8 minus 6.
Okay.
This polynomial division.
I think factoring for division feels better to do.
So let's say that
We don't need a good
again, someone
numerator.
walks up to the screen and says, "What is x squared?" The express this is the numerator. What I can think of is constructing a difference of squares using x plus 2. So we know that x plus 2 times x minus 2 is equal to x squared minus 4. So what if we were to write x squared minus 4 up here, and then we would just have to add 5 to get to plus 1. So what if we were to write x squared minus 4, and then we write plus 5. This expression and that expression up there, those are completely equivalent.
Oh.
Why did I do that? Well, now I
Yeah.
can write x squared minus 4 as x plus 2 times x minus 2. And so then I could rewrite this entire expression as x plus 2 times x minus 2. All of that over x plus 2 plus 5 plus 5 over x plus 2. And now as long as x does not equal 2, then we could divide the numerator and the denominator by x plus 2. And then we would be left with x minus 2 plus 5 over x plus 2.
Ah.
That would be straight. I want to say that this expression is the same as that first expression. Or x does not equal, or x not equaling 2. And so here, we say, hey, x squared plus 1 divided by x plus 2 is x minus 2. And then we have a remainder of 5. Of 5. Now let's do the same question, or try to rewrite this using algebraic long. We'll see that this is actually a little bit more straightforward. So we are going to divide x plus
Okay, so like, okay, so you like change that, you extend this, complicated that to where it makes the bottom one be, okay. Divide polynomial expressions, a using long division, divide the highest degree term of a with the highest degree term b, give the term of the quotient, multiply the result of step 1 by b, subtract the result of step 2 from a, be careful when subtracting negatives, repeat the divide, multiply, subtract steps using what's left from dividend until you get a result is lower degree than b. And the terms calculated and then the divide steps, quotient q and the left row on the yeah. Quotient be that. Okay, let's try. Okay, I'm gonna try both ways, the factorings and this. X squared and x plus 3. Okay, long division first. X squared and x plus 3. Now I'm just gonna do that. Okay, so that goes into it 2 times. It goes like 2 times, and then multiply that, and it gets like 6. So like 2, and then that goes 6. And then 2 times 2 becomes like 2x plus 3, and then like that, 2x minus that. multiply the result of step 1 by b, which is 6. Subtract the results of 2 from a, and x minus. Okay, x plus 6 minus that goes to x, and then 6. Because 6 doesn't get divided by any. So that would be like 2 plus 6 divided by x plus 3. This does not look correct. Okay, let me try the factoring. Okay. Both those together would equal to x squared. What is that? X squared plus 3 and x squared minus 3 would be equal to 9. 9, so then we just 9, so x squared minus 9, and then x plus 3, x squared minus 9, this two together, which then can become plus, which can become x plus 3 and x minus 3, and then that becomes, that gets cancelled out, and then leaves with x minus 3. X minus 3. Oh, you just add like another, you just randomly added a 0x. First we're gonna get a divided. Okay, so you can just add a 0. You can just add like a 0 into that. Let me try again. X squared divided by x plus 3. Okay, so then it becomes x plus 3 to x squared plus 0 x goes into that. X times 1, I guess. And then it becomes x squared. And then multiply that by that, and then x squared. Okay, I'm gonna close this so I can. X squared plus 3x, and then you subtract it by that. That cancels out, and then you get negative 3x. X goes into negative 3x, negative 3 times. Negative 3. Then you multiply. And then you multiply that with that. Negative. X negative 3x minus 9, and then that cancels out. That cancels out, and then again negative 9 as the remainder. Then you get the plus 9 divided by x plus 3. Okay, I did it. I got the right answer. Okay. Now why did that 9 turn into okay, negative 0, negative 9? Oh yeah, okay. The subtracting thing. Okay. I might understand it now. I might understand it. The numerator is and the rational expression above the numerator is a third degree. In the polynomial, the diagonal of first degree polynomial, therefore the quotient must be a second degree polynomial. In the first term of the quotient, we must divide the highest degree term with the numerator. Highest numerator is 6. X to the third power. Size of each. No, that's correct. First term of the quotient is 2x 3x 3x. Darn it. Is it literally just 2x? That thinks from the numerator, the mathematical expression is that. Different numerator is a third one, yeah. Oh, I didn't add the power. Okay, I got close to it, I guess. Okay, that times that. And this cancels out, and then 2 this. Yes. Okay, factor those. minus 1. X plus 6 and x minus 1. That should not... It's gonna be plus 3 plus 2 or something. Plus 2. Because that's gonna cancel out. It's gonna have to cancel out with that. And then... x, and then x plus 4. X plus 4. And then cancels out with that, so then just x, and then it's gonna cancel out with 3. And then it's gonna be x squared plus 2x. Yay. And get subtraction. Okay, so we gotta put them together, which is 8x minus 12. 8x minus 12. Yeah. Minus 3x plus 3. Okay, and then it's gonna be these two together. It's like 2x squared plus negative 3x plus 2x, which becomes plus x, and then negative 3. And then simplify this, minus 3, 5x. That becomes 9, and then okay, so then we just gotta simplify this again. 2 minus... Okay, what is that? 2x plus 2, x minus 2, x plus 3, x plus 3, and x plus 3 times x minus 2. Did I multiply that? Did I multiply this correct? 2x squared, negative 3, 2x, negative x, then negative 3 plus 2. What did I do wrong? What did I do wrong on the top? this? What did I do wrong? 15? How did I get 15 not? How did, okay, let's try again with this one. Okay, division. That seems like it can be, that's factorable. It's gonna, what will it equal to? Okay. 5. 2 plus 2 plus 1 is, that's not gonna get to 5. So we're gonna have to do the long division. Okay. X plus 5, and then x squared plus 5x plus 2. Okay, that goes into it. X times and x squared plus 5x. And then it cancels out. Then there's 5x. But that's also 5x. I guess that cancels out to 0. X goes into 0 times. And then that's 0 plus 0. And then that's 0, 0 minus 0, 0. And then 2, x goes into 0, it's 0 times? What is x? Okay, so no. Okay, so 5x. Back to 5x. Goes into a 1 time. No, it's gonna go 5. 5x times. No. Okay, 1 time. And then x plus 5 minus, subtract that, that's going to become 4x. No, it's going to have to be 5, it's a 5x. And then multiply that, okay, no. Remove the 5, and it becomes 5x, and then 15, 25, and that cancels out, do that, and then 20, 25 goes into x. 25 I wonder if writing it down is going to make it any easier. I wonder if writing it down is going to make a difference. X plus 5 divided by this. X and then X. 5x. Subtract it. Cancels out, cancels out. I guess we cancels out. It doesn't make 6. 2. Guess goes into 1 time. But then x plus 5. Subtract it. You can. I don't know. Is it C? Okay, I figured it out. I'm losing it. This is the first lesson in this part, and I'm already losing it.
Which expression is equivalent to the above difference? All right, this is going to be fun. So we're adding these two, I guess we could say, rational expressions. And when you add two expressions like this, if you add any fractions, you want to have a common denominator, and the same thing is true over here. And so one thing we can do is let's actually see if I can maybe write that. So 3 over x squared plus 5x minus 24 minus 7 over x minus 3. Now instead of, what the brute force way is just multiply the denominators, say, okay, that's going to be a common multiple. But there might be a cleaner way of doing that, especially if x minus 3 is one of the factors of this. So let's see if this is. So let's see. Negative 3 times positive 8 is going to be negative 24. And the negative 3 plus positive 8 is positive 5. So this actually can be factored into x plus 8 times x plus 8 times x minus 3. This is what this thing is. And if this step looks unfamiliar to you, I encourage you to watch the video on factoring quadratic expressions. But what's neat about this is now we say, okay, look, to have the same denominator here, we just have to take this fraction and multiply the numerator and denominator by x plus 8. If you multiply the denominator by x plus 8, then these two denominators are equivalent. But I can't just multiply only the denominator by x plus 8, I also have to multiply the numerator times x plus 8. And so what does this simplify to? This is going to be equal to 3 over x plus 8 times x minus 3. And then minus, that's going to be 7. Minus, with this negative sign, x minus 2. Minus 7, actually, let me just write this. Minus 7x plus 56 over x plus 8 times x minus 3. I was really understanding this because I would probably do all of these steps. I would try to change the fractions. So this is what we will do. We have our common denominator, x plus 8 and x minus 3. So it's going to be 3 minus 7x minus
Okay. X plus 1 6 squared the minus in the other part. And that's going to become 6x squared plus 2x. Then minus 3x. 3x goes into 1 time. Negative 3x minus 3 is 1. Again. And then negative 1 is a remainder. And which is d. Okay, maybe long division is actually better. If it's g, then I think I understand. If it's g, then I understand it now. Okay, it is d. Yay. Okay, let's do this. Okay, so this is just simplifying. Common, okay, no, not 2, 7. So everything is going to be equivalent to 7. That's 6. That's going to be 7. 2. So this. Another simplifying, and another common factor. 12 is 12. No, 12 is it's not going to be equivalent of 12. 6. It's not equivalent of 6. 2. That's 7. Yeah, 7. 8. 9. 9, so this is the right one. Why are these questions significantly different than the ones that I was doing in all of that before? All of these are just simplifying. These are common factors. And anyway, 11, negative 5, plus 7. And then say minus 4. Why is this different? Finally, this is equivalent to multiplying. This is equivalent to multiplying from x plus y divided by 2 times 2x plus y times 2x plus y is equal to 4b. Why was all of that irrelevant to what was that? Huh? Okay, what is it? Let's do this. What are the solutions to the given equation? Okay, so put it together into... Okay, so... Okay. Common factors, 2, so 2 is similar, 5 not, okay. Divided by 2, 20, 25, 52 divided by 2, 4, no, 2, 2, 4, 6, no, 8, 10, not 10, can it be 8? No, so 2, so it's going to be, they can be simplified to 2, it's 25 and 16, and then you gotta like isolate x. Wait, is 32 readable? 32, no. Okay, so 25 over 16, and then one of the, to isolate x, you need to be, one of them is going to be negative, so okay, let's move on x. I'm gonna crash out. If it's this. Okay, look for the common factor, yeah. And then, we just simplify like that. And then, okay. So what value of x is the expression this undefined? And it's going to be when the bottom is going to be equal to 0, and then if that's equal to 0, 7 has to equal to 4. X is going to have to, this is going to be 4, so. What would make this negative 4? What would make this 0? 7 times 5, 6, 8, 5, 7. One 5. Okay, this needs to be a fraction. Okay, so 4 divided by 7. Okay. Okay, what is the solution to these equations? This I can just put in the calculator. This I can just... This I can just plug in. And that's gonna be... That's okay. 2 negative 13. Yeah. Again, I just plug it in to 1/2 squared plus 1/2 1 L what's the fuck in terms of L. Okay, so we divide, so L divided by 2, and then it comes W plus 1 is equal to 1/2, and then W equals to 1/2 minus 1. No, L. No, wait, yeah. This. L. Okay, what is this? Equation n is constant, if the equation has solutions of this, so the value of m. Well, part of this will make that. Okay, so this is associated with that. This is associated, and then this is gonna have to. So that's a 9. That's multiple of 3. So then 2 is gonna have to be times 3. That's gonna be 6. Where y equals u and y equals d, b makes solution to a solution, but it's the value of u times d. Okay, so y is going to equal to 1/2. 1/2 times 8, like 4. What is the solution? What are the solutions to a given equation? W2 is equal to 2x squared, either negative 6 or 6. And then you give an equation, a is a constant. What is the value of a? If the equation has solutions of x equals 3 and x minus the value of a, x minus 2, and then that's going to be, so it has to equal to plus 4 minus 4. So negative 2, no, that's, yeah, like times negative 2. Oh my god. Okay. What? So it has to equal to... Is it... Oh, no, okay, it's just 2, it's just... Okay. What are the solutions that they do in an equation? 3 divided by 7, that's 9. 9, okay, n equals 3. I'm gonna lose it. In what's world? In what world will negative 3 be? I don't know, it is gonna be, yeah, that's because it's squared. Okay. If I could use solution to the system, when you go B, that's 1. Consider the following system equations. Okay, it's constant if the solution to the system equations are in points 0, 3, and 5, 0. What is the value of k? 3. Now, what makes this? If the solution equations are in the points. Now what makes this fractions? What makes this fractions? What makes it a negative fraction? Because then the problem is from my equation. Right, so we pass it a point, not. We pass it not. If constant solutions in the system equations are okay. Which of the following solution system equations? Again, I can just plug. I should be able to just plug this in. And positive 2, negative 3, negative 13. Yeah. So let's define solutions. Negative 4, 3, and negative 1, negative 3. 1 and 3. Okay. What is the solution? That's 4, 0, 4, 0, 4. If it's anything other than 0, 4, then I'm gonna scream. I'm gonna freaking scream. I'm gonna crash out. I would have crashed the okay. Good. Good. Okay, let's see this test. Let's see what's what's the best interpretation of the ordered pair of that? 2009. It's gonna be at a decreasing rate of that. No way. It's gonna be approximately. Yeah. The graph, what are the points? So the zeros of f. Negative 3, 0, only. If we try to the point, what's the value 0. The graph of dash on an x-way, which one is exactly which of the graph is a constant coefficient of the y-intercept. The graph of dash, which the following characteristic of the graph is a constant coefficient in the equation of rhythm, is a constant, the y-intercept. Yay. Okay. Okay, 0, 0. Value of 0. Okay, this becomes 0, this becomes 0, this becomes 0, 1. Not 12, 1. Haha, 1. There's the following equivalent to that. 2x is this. Okay, so 2x to the third power. That doesn't really help. Okay, so okay, what about this? 4. Okay, so is that multiplying or is that adding 2 to the 7th? No. 2 to the 3rd. Okay, so it's specifically multiplying the exponent. It's specifically multiplying the exponent, so it's going to be this. Quadratic graphs, which define equations to be paired with the system equations, so it's which of the following equations can be paired with a graph equation that is create a system of equations where the solution is comprised of points 2, -2, and -33. So that's 1 is decreasing slope. Okay, the value of C. C is positive as the value of C. that becomes 20, that becomes 25, so this is gonna have to equal to like 8. Which is as x increases by 1, it decreases by 0.5. No, it halves. This. What's the equivalent of form of? What is the equivalent of form of? Which of the following is the equivalent form of blah blah blah? -5 and +9. Okay. Based on the model, 1,000 is city X and city 10. 81.05. So, 2 years after. Then that's 10 years. Roughly 130. Which of the solutions to given? We already said it was this. Which of the following is equivalent to the? Which of the following expression is equivalent to that? Okay, simplify it. 9. 1, 1, 5, 5, and this. If that is going, what is the express part? The first you multiply on the other side. So 11 pt. 11 pt divided by 11t. What are the coordinates of the y-intercept? 0, 1. The function is h is defined. What is the value of h? If root and 4 times 9 is 36. 6. I don't think we need to go into rationals, into exponents. How long is okay, so it's equivalent. Okay, this is equal to that. It's more specifically exponent. X. And then okay, let me take this test again. The value is A. 11 is going to be 3 over 4. Yeah. 2 over 4. No, it's going to be 1 over 4. What is the value of x? Okay, what is the value of x? This is all of that's going to equal to that, so this adds together, but then it's going to become 4 plus, that's going to be 6. 9. Crap. Okay, so 8, 9, 10, 11. Okay. Okay, so it seems like... Okay. Value of A, 1 over 7. Okay, it does not eat it. What is the following expression is equivalent to the given expression for all A doesn't equal 0? Okay, so it's gonna multiply together, so 6, and then 6, no. It's gonna be 18. No, wait. Okay, so it's gonna multiply by 9 times. 9 times. 6. But then where's the negative go? Where does negative go? That becomes either 6 or 9, and then 6, 2. Got it. Okay, we're gonna move on from this one lesson. We'll move on from this unit to... What's the next one? This one. Geometry and trigonometry. Okay, that's 56. BC. Okay, so it's like 8. Okay, so 5 squared plus x squared is equal to 6 squared. 6 squared. So it's gonna be our roots from the looks of it. What's root 61? What is root 11? It's root 11. Okay. Formulas, blah blah blah. 6 long, 2, okay, so 20, 21 to 120. Okay, ABC is shown. What is tan? BAC, BAC. So Haktoa. So adjacent and opposite. So opposite divided by adjacent, so 4 divided by 5. Yeah. 93. Okay, then this is gonna have area shaded sector with area of a circle. Central shaded sector measures 135 area shaded sector with a fraction of the areas the circle. Is it 135 divided by 360? Oh, okay. Circles equal to pass to the center. Okay. So H and K, so it's going to be +1. It's going to be +1 the center is going to be +1, and then it's going to be it's going to be +1, and then I think it was, what was it, squared or point? I guess the top is going to be equal to either, it's going to be, okay, it's going to be one of these two. I'm going to go with A. So it is 64. Okay. Equation suggests the square of the radius is 8. This equation suggests the square of 8. Okay, so it is. Okay, so you gotta square it. Understood. Which of the following radian measures is equal to 360? Pi radians. 2 pi radians. The circle x from then, the radius 9 and so on. There's the equation of the circle. So it's going to be this, and then it's going to be this. Okay. Which defining degree is equal to x pi radians. Circle the radians circles, so it's going to be half. Okay. So I need to learn and study the. So I gotta focus on these circle theorems. Circle theorems or problems are all about finding arc lengths of various angles and circles, unless okay.
And circle here, whose circumference is 18 pi. So we would have measured all the way around the circle, we would get 18 pi. And we also have a central angle. So this is the center of the circle, and this central angle that I'm about to draw has a measure of 10 degrees. So this angle right over here is 10 degrees. What I'm curious about is the length of the arc that subtends that central angle. So what is the length of what I just did in magenta? And one way to think about it, or actually the way to think about it, is that the ratio of this arc length to the entire circumference, we write this down, arc length to the entire circumference should be the same as the ratio of the central angle. So the central angle to the total number of angles, we go all the way around the circle. So to 360 degrees. So let's just think about that. We know the circumference is 18 pi. So we know the circumference is 18 pi. We're looking for the arc length. I'm just going to call that A for arc length. That's what we're going to try to solve for. We know that the central angle is 10 degrees. 10 degrees over 360 degrees. Over 360. So we can simplify this by multiplying both sides by 18 pi. Multiply both sides by 18 pi. And we get that our arc length is equal to 10 over 360 is the same thing as 1 over 36. So it's equal to 1 over 36 times 18 pi, which is just, so it's 18 pi over 36, which is the same thing as pi over 2. So this arc right over here is going to be pi over 2, whatever units we're talking about, long. Now let's think about another scenario. Let's imagine another, for the same circle. So it's the same circle here. Our circumference is still 18 pi. Circumference is still 18 pi. There's a lot of comments behind here, so I'm sorry about those long voices. But this circumference is also 18 pi. So this is also 18 pi. But now I'm going to make the central angle, I'm going to make it an obtuse angle. So the central angle now, so let's say we were to start right over here. This is one side of the angle. I'm going to go and make a 350 degree angle. So I'm going to go all the way around like that. So this right over here is a 350 degree angle. And now I'm curious about this arc that subtends this really huge angle. So now I want to figure out this arc length. So all of this, I want to figure out this arc length, the arc that subtends this really obtuse angle right over here. Well, same exact logic. The ratio between our arc length A and the circumference of the entire circle, 18 pi, should be the same as the ratio between our central angle that the arc subtends, so 350, over the total number of degrees in a circle, over 360. So multiply both sides by 18 pi. We get A is equal to, this is 35 times 18 over 36 pi. This is 350 divided by 360 is 35 over 36. This is 35 times 18 times pi over 36. Over 36. Well, both 36 and 18 are divisible by 18, so let's divide them both by 18. And so we are left with 35 over 2 pi, or we can even say, let me just write it that way, 35 pi over 2, 35 pi over 2, or if you wanted to write it as decimal, this would be 17.5 pi. Now, does this make sense? This right over here, this other arc length, when our central angle is 10 degrees, this is an arc length of 0.5 pi. So when you add these two together, this arc length and this arc length, 0.5 plus 17.5 makes 18 pi, which was the circumference, which makes complete sense, because if you add these angles, 10 degrees and 350 degrees, you get 360 degrees in a circle. Let's think about another circle. Let's imagine another, or the same circle. It's the same circle here. Our circumference is still 18 pi. Circumference is still 18 pi. There's circumference behind here, so I'm multiple places. But this circumference is also 18 pi. But now I'm going to make the central angle pi
I'm going to make it an obtuse angle. So the central angle now, so let's say we were to start right over here, one side of the angle. I'm going to go and make a 350-degree angle. I'm going to go all the way around like that. So this right over here is a 350-degree angle. And now I'm curious about this arc that subtends this really huge angle. So now I want to figure out this arc length. So all of this, I want to figure out this arc length, the arc that subtends this really obtuse angle right over here. Well, same exact logic. The ratio between our arc length, A, and the circumference of the entire circle, 18 pi, should be the same as the ratio between our central angle of the arc subtends, 350, over the total number of degrees in a circle, over 360. So multiply both sides by 18 pi, we get A is equal to, this is 35 times 18 over 36 pi. This is 350 divided by 360 is 35 over 36. This is 35 times 18 times pi over 36. But both 36 and 18 are divided by 18, so it's divided by 18. And so we are left with 35 over 2 pi, or we can even say, let's write it, 35 pi over 2, 35 pi over 2, or if you wanted to write it as a decimal, this would be 17.5 pi. Now does this make sense? This right over here, this other arc length, when our central angle was 10 degrees, this had an arc length of 0.5 pi. So when you add these two together, this arc length and this arc length, 0.5 plus 17.5, you get to 18 pi, which was the circumference, which makes complete sense, because if you add these angles, 10 degrees and 350 degrees, you get 360 degrees in a circle.
I do not understand any of this.
A circle with area 81 pi has a sector with a 350-degree central angle. So this whole sector right over here, this yellowish color, that has a 350-degree central angle. So it's a very large angle. It's going all the way around like that. So yes, what is the area of the sector? So we just need to realize the ratio between the area of the sector.
So 10,
Sector. The ratio between the area of the sector.
350 divided by 360.
Cancel out. 350 divided by 360 is 35 over 36. And so our area, our sector area is equal to, see the numerator, we have 35 times, instead of 81, I'm just going to write that as, let's see, that's going to be 9 times 9 pi. And the denominator I have 36, well that's the same thing as 9 times 4. And so we can divide the numerator and denominator both by 9. And so we are left with 35 times 9, and neither of these are divisible by 4, so that's about as simplified as we can get it. So let's think about what 35 times 9 is. 35 times 9, it's going to be 350 minus 35, which would be 315, I guess. 315, did I do that right? Yeah, it's going to be 270 plus 25, which is 315 pi over 4. 315 pi over 4 is the area of the sector.
Okay. Okay. Goodness, you don't need to know farmers just took it sort of at the beginning of Egypt. No. Yeah, it's gonna find. Okay. The central angle is circumference by 2 radii. The angle lets us divide a portion of the circle's circumference, an arc, therefore the portion of the circle's area, a sector. The number of degrees in the arc is circle is 360 since it's circumference, and area both describe the full 368 degree arc of a circle. We can set up proportional values between the parts and the holes of any circle. Yeah, okay. And the figure so 950 area circle is 16. This area circle is 16 pi. What's the area? Okay, so equal to that. That is 90, 360, and okay, so area arc length is 16. 16 pi over over, is this over pi? Okay.
35 times 9.
Area, okay, so sector area, okay, so it goes to 16, and then this is x, okay, then you, this gets pi, and then get rid of, so then it becomes 9 times 16. You can multiply that for 4 times 4 pi, and then 36. 36, that's, this can be turned into like 9 times 4, which cancels that part out, so then it becomes 4 pi. Nice. Okay. Point A is the center of link RPC. The species is 3 over 10 of the circumference of the circle with value as x. Three divided by 10 has to equal to 360. Okay, so 360 divided by 10, 36 times 3, 108. This is, okay, so 108. Okay, I did it. Okay, figure above, was the center of the circle. In fraction of the entire circle is over by the shaded region. 150 over the should be proper fraction 360. If the length of my arc is 10, what's the circumference of the circle? Okay, so 10 divided by that, and then it's equal to, which is equal to 150 over 360. Or does it go? Okay, no. The arc goes down here, so then it goes 150 divided by 360. Fraction that, 5 over 12. Okay, no. 10 pi is equal to that. Times 10. That doesn't help. Okay, so... Okay, no. It's 10 divided by whatever pi. Okay. Multiply that by double it, that's like 24. I'm so cracked. I'm so cracked. I am so cracked with this. Okay. Angle relationships. Sometimes we'll be asked to apply our knowledge of angle relationships to angles within... Sometimes we'll be asked to apply the knowledge of angle relationships in angles in a circle. Additional 2 common angle relations in theory. The question will also ask for circle-related facts. The first we've already covered in previous sections. Some central angles is measured by circle 360. Second, of the radii of same length. The training triangle between the two is an isosceles triangle. Training triangle. And second is that since all the same length, any triangle that contains 2 radii is an isosceles triangle. For example, the radius of a circle, so OA is equal to OC. Triangle AOC is an isosceles triangle. The measures of the OAC and OCA are both 30. So it's not... Okay, let's figure it out. So the circle is the value of x. It's both taken up. So 50, 50, and then 100. It's going to equal 80. So that's 80. 80. 360 minus 80. 360 minus 80. 280. Nice. Okay, measure of angle of BAO. Okay, so it's 35. 35. Measure of AOB. 180 minus 70. 110. Angles AOB and COD are complementary. What is the value of x? 35. I'm gonna crash out. BAO 35. AOB 110. Supplementary, vertical angles. What is it? Circle. The circle has 12 pi. What is the minor arc of AC? Divided by times. Equal to 12 pi, and then 360, 120. So then comes 12 divided by 36. And then times 6 times 2 pi, and then this becomes 6 times 6. We can also simplify this. 6 times 2, and then both 6's gets taken out. it becomes 4 pi. Yay. Circle is the area is 3/8 of the area of the circle. What is the value of x? Three divided by 8. 360 times 3/8. 135. Cool. The figure above, O is the center of the circle, and AC is the diameter. What's the value of X? Okay, this is isosceles. This is a perfect straight angle. So then it's gonna be. So since this is diameter, it's gonna be. This is 180. 25, 25. This is 180 divided by 180 minus 50. 180 minus 50. 130, and then 130, 50. Yay. Circumference always has pi, arc length is static. Okay, that's actually not bad. That's actually not so bad. Okay. Length of ABC. So it's like 135 over 360. 130. So it's like 135 over 360, which is essentially 3/8. Where did this come from? Oh wait, it's gonna. Okay, it's equal to the something pi divided by something pi. Okay, circumference, circumference is 2x, negative 2 times pi times 3, yeah, it becomes 6 pi, and then, okay, then you 135 divided by 360, and then you times it by 6, 6 pi. We can probably we can separate this. What's gonna be, okay, so it's, like 36, 10, 36, 10, separate this by, 6 times 6, and then, so then you cancel these out. Cancel those out. Is there any way to simplify that? No. So this is 60. What about? Okay, well, that becomes 60, and then like 5 times 12. This can be simplified. This can be 135 divided by 5. 27 times 5. 27 times 5. Both 5s cancels out. Can you simplify 27 and 12? I don't think you can. No, 3. 3 times 4. 3 times 9. 3 times 9. The 3s cancel out. Nine root over 4. A 9 pot. Oh, yeah.
All the way around. And let's see. We divide 107 divided by 3 is not 5 inches. Or we can multiply it.
Oh, yay! I got it right. Okay, circumference 10 pi, arc x, the circle central angle is 6. So 10 pi is equal to 260 over 360. Okay, then 26 times divided 26 times 10. Times 10 pi, and then 36, 6 times 6, and then what's 26? 2 times 26, 10, 3, 13. Let's turn this into something else, like 2 times 36, 18. The 2's cancels. These 2's cancel out. And then this becomes 9 times 9. Or 9 times, no, 2 times 9. 2 times 9 then becomes 2 times 5. Can't give 2's. And then this becomes, what is this, 60, 65, 65. Which, what is 65? Oh no, wait, we can end it here because that's already an answer. 65 divided by 9.
That's all I did there. So 65 divided by 9. It was like, that's simplifying it. That's nice. That's one of the choices.
Yay.
The circle has a circumference.
I understand it now. Okay, what is the minor arc is what fraction of the circumference of the circle? 120 divided by 360. Yay. What area is what the area shaded is what fraction of the area of the circle? Okay, so 225 divided by 360. Simplify that to 5/8. Okay, so then what fraction of the circumference is the circle? 150 this time. 512. The area of the shape is a fraction of what area of the circle? 60. 6. Okay, so area of the thing and the arc. Okay, so arc length is equal to circle area. That's good to know. Yay. Okay, trigonometry. Problems with lesson above equals radii. How do I convert between radians and degrees?
Let's see if we can give ourselves a practice of converting between radians and degrees and degrees and radians. And just as a review, just remind ourselves of the relationship, and I always do this before I convert. Like one revolution of a circle, how many radians is that? We know one revolution of a circle is 2 pi radians. And how many degrees is that? Like one revolution around the circle. We know that that's 360 right? 360 that quite right. Just like that. And this is really enough information for us to think about how to convert between radians and degrees. If you want to simplify this a bit, divide both sides by 2. Pi radians are equal to 180 degrees. Or another way to think about it, going halfway around the circle of radians is pi radians. The arc that subtends that angle is pi radiuses, and that's also 180 degrees. And if you want to really think about, well, how many degrees are there per radian? You can divide both sides of this by pi. If you divide both sides of this by pi, you get 1 radian. Singular, plural, singular, 1 radian is equal to 180 over pi degrees. So all I did is I divided both sides by pi. And if you want to figure out how many radians are there per degree, you can divide both sides by 180. You get pi over 180 radians. Radians is equal to 1 degree. So this is, now I think we are ready to start converting. So let's convert 30 degrees. Let's convert 30 degrees to radians. Let's think about it. I'm going to write it out. And actually, you might remind me of the analysis that might be. But it also works out here. So if I were to write 30 degrees, this is how my radians like to work with it. I like to write out the word degrees. And I say, well, I want to convert to radians. So I really want to figure out how many radians are there per degree. So I'll write this down. I want to figure out how many radians are there. How many radians do we have per degree? I haven't filled out how many that is. But we see just that units will cancel out. If we have degrees times radians per degree, the degrees will cancel out. I'll be just enough radians. If I multiply the number of degrees I have times the radians per degree, we're going to get radians. And that makes more sense as well. And here we just have to think about, well, if I have, think of it this way, if I have pi radians, how many degrees is that? Well, that's 180 degrees. Comes straight out of this, right? Pi radians for every 180 degrees, or pi over 180 radians per degree. And then this is going to get us to 30 times pi over 180, 30 times pi 80, which will simplify to 30 over 180 over 6. So this is equal to pi over 6, which is equal to pi over 6 radians. Now let's go the other way. Let's think about if we have pi over 3 radians. Pi over 3 radians. Now I convert that to degrees. So what am I going to get? Well, here we're going to want to figure out how many degrees are there. How many degrees are there? It is, well, pi for every 180 degrees. 180 degrees per radians. 180 degrees per pi radians. So this is 2 multiplied by 1. So radians is about pi is about 180 over 3 is 60. Now let's think about 45 degrees. 45. That relation as well. How many radians will this be equal to? Well, once again, we're going to think about how many radians we have per degree. So times. We know we have pi radians. We have pi radians for every 180 degrees. Pi radians for every 180 degrees. And here, let's do the degrees cancel out. By that word, we're about 45 pi over 180 radians. 45 degrees times we have pi radians for every 180 degrees. So we are left with 45 times pi over 180 degrees. It's about which is equal to 45 half 9, which is half 180. So pi over 4 radians. Let's do 1 more. So say that we have negative pi over 2 radians. What's that going to be in degrees? Well, once again, we figure out how many degrees are each of these radians. We know that there are 180 degrees for every pi radians. For every pi radians. So we're going to get radians cancel out, pi's cancel out. So you have negative 90 over 2. This is negative 90 degrees. Think about that. I'll do more examples.
Okay, I think I kind of understand it. Radian measure. Okay, so radian measure. Okay, 90 divided by 180 is equal to pi. And then this is x, so we gotta isolate x, and then 90 pi. 90 pi is equal to... Okay, so which basically is equal to x. Simplify this is gonna be 1 pi over 2. Nice. That's all. I mean, you can use radians to calculate arc length in sector, so it's like in measures. Circle angle, central angle. Arc length is central A or B has a measure of 2 pi over 3 radians. What is the area of sector formed by central A or B is action of the circle, so we get we'll turn it into we'll turn it into 180. Okay, 2 pi divided by 3 is equal to 180 divided by pi. The pi cancels out. And then the ratio wise, $180 times 1.12 divided by 1/3. 300 over 300. 300, 1 divided by 80. 180 divided by 300. What is that? 3 over 5. One-third. Central angle. What is that? Central angle is equal to that. Okay, central. Okay. Order from the smallest to largest. So this is the smallest, and that's gonna be the smallest. 20. Okay, so 20 is equal to 5 divided by 180. 20 pi, that 20 pi, that gets simplified. 20 pi, that gets simplified to 1. This gets simplified to 9. So pi over 9. So this is smaller than the third. And then 55. 55. 180. 180. divided by 5. 36. 6, and then this becomes 11. 11 over 36. Can simplify that a little more. 11. So yeah, come on. Okay, let's do it the other way. Radians to degrees. 12. Okay, so divided by 12 is equal to 180. 180 divided by pi. That gets cancelled out. Pi's get cancelled out. Gotta use the bathroom. Okay. Okay, what was the original way? What was the original way? Okay. No, that's
We're going to want to figure out how many degrees are there. How many degrees are there? That is, well, pi radians. For every 180 degrees, every 180 degrees, pi radians. These are essentially the same thing. It's essentially just 1, which means radians cancel out, and pi cancels out. We're left 180 over 30 degrees. Very good. So this is 60 degrees right now. 60 degrees, 90 degrees, 60 degrees. Now let's think about 45 degrees. 45.
okay. Everything cancels out at the end. 180 divided by 12, 15. So 15. Okay, 15. So 15 degrees, 20 degrees. Degrees, 20 degrees. Okay, I'm gonna just turn the mic off for a bit.
Centered at point A, and the point B lies on the circle, and then we drop the perpendicular from point B to point D. Point D lies on the positive x-axis. So they form the triangle ABD, and they tell us an angle BAD, angle bad, it has a measure of pi over 4 radians. What I want to do in this video is use our knowledge of trigonometry and use our knowledge of triangles in order to figure out several things. So the first thing we want to figure out is what's the measure of angle, what's the radian measure? What's the radian measure of angle ABD, Actually, we'll just do that first, and then I'll talk about the other things that we think about. So I assume you paused the video and tried to do this on your own. So let's think about what ABD would be. You know two of the angles of this triangle, so if you know two of the angles of this triangle, you should be able to figure out the third. Now, it might be a little bit unfamiliar. We're used to saying that the sum of the interior angles of a triangle adds to 180 degrees, but now we're thinking in terms of radians. So we could say that the sum of the angles of a triangle add up to, instead of saying 180 degrees is the same thing as pi radians. So this angle plus that angle plus that angle are going to add up to pi. So let's just say this right over here. Let's just say measure of angle ABD in radians plus pi over 4 plus pi over 4 plus this is a right angle. What would that be in radians? Well, a right angle in radians, a 90 degree angle in radians is pi over 2 radians. So plus pi over 2. When you take the sum of them, the interior angles of this triangle, they're going to add up to pi radians, which is of course the same thing as 180 degrees. And now we can solve for the measure of angle AB. Measure of angle ABD is equal to pi minus pi over 2 minus pi over 4. I just subtracted these two from both sides. So this is going to be equal to, we put a common denominator of 4. This is 4 pi over 4. This is minus 2 pi over 4. And this, of course, is minus pi over 4. So 4 minus 2 minus 1 is going to get us to 1. So this is going to get us to pi over 4. So the measure of angle ABD is actually the same as the measure of angle BAD. It is pi over 4. So that angle right there is pi over 4. Now what does that help us with? So if we know that this is pi over 4, that is pi over 4 radians. And once again, we know this is a unit circle, so we know the length of segment AD, but this, which is the radius of the circle, is length 1. What else do we know about this triangle? Can we figure out the lengths of segment AD and the length of segment DB? Well, sure, because we have two base angles that have the same measure. That means that the corresponding sides are also going to have the same measure. That means that this side is going to be congruent to that side. I can reorient it in a way that it might make it a little easier to realize. If we were to flip it over, if we were to, like, not completely flip it over, but if we were to make it look like this, so the triangle, we can make it look like, let me make it a little bit, a little bit more like this. Actually, I want to make it look like a right angle though. So my triangle, let me make it look like, there you go. So if this is D, this is B, this is A, this is our right angle. Now this is pi over 4 radians, and this is also pi over 4 radians. When your two base angles are the same, you know you're dealing with an isosceles triangle. An isosceles, because they're not all the same, you know it's not equilateral. All the angles are the same, this is an equilateral. This is an isosceles non-equilateral triangle. So if your base angles are the same, then you also know that the corresponding sides are going to be the same. These two sides are the same. This is an isosceles triangle. So how does that help us figure out the lengths of the sides? Well, if you say that this side has length x, that means that this side has length x. If this side has length x, then this side has length x. And now we can use the Pythagorean theorem. We can say that x squared, this x squared plus this x squared is equal to the hypotenuse squared, is equal to 1 squared. Or we could write that 2x squared is equal to 1, or that x squared is equal to 1 over 2, or just taking the principal root of both sides, we get x is equal to 1 over the square root of 2. And a lot of folks don't like having a radical in the denominator, don't like having a rational number in the denominator. So we could rationalize the denominator by multiplying by the square root of 2 over the square root of 2, which would be, so the numerator will have the square root of 2, and in the denominator, we're just going to have square root of 2 times square root of 2 is just 2. So we've already been able to figure out several interesting things. We're able to figure out how to measure angle ABD in radians, we're able to figure out the lengths of segment AD and the length of segment BD. Now what I want to do is figure out what are the sine, cosine, and tangent of pi over 4 radians, given all of the work that we've done. So let's first think about what is the sine. We'll do this in a color orange. Given all the work we've done, what is the sine of pi over 4 radians? And I encourage you once again, pause the video, think about the unit circle definition of trig functions, and think about what this is. Well, the unit circle definition of trig functions, and this angle is pi over 4 radians, is forming an angle with a positive x-axis, and where its terminal ray intersects the unit circle, the x and y coordinates of this point are what specify the cosine and sine. So the coordinates of this point are going to be the cosine of pi over 4 radians is the x coordinate, and the sine of pi over 4 radians is the y coordinate, sine of pi over 4. So what's the y coordinate going to be if we want the sine of pi over 4? Well, it's going to be this length right over here, which is the same thing as this length, which is the length of x, which is square root of 2 over 2. Now what is the cosine of pi over 4? And once again, I encourage you to pause the video to think about it. What's this x coordinate? What's the x coordinate? The x coordinate is this distance right over here, which is once again going to be x, which is square root of 2 over 2. Now, what is the tangent of pi over 4 going to be? Well, the tangent of pi over 4 is just sine of pi over 4 over cosine of pi over 4. Now, both of these are the exact same thing. They're both square root of 2 over 2, so you can have square root of 2 over 2 divided by square root of 2 over 2. Well, that's just going to give you 1. And that also makes sense, because remember, the tangent of this angle is the slope of this line. And we see the slope for every x we move in the horizontal direction, we move x up. So our change in y over change in x is essentially x over x, which is equal to 1. what I have attempted to draw here is a unit circle. And the fact that I'm calling it a unit circle means it has a radius of 1. So this length from the center, and I centered it at the origin, this length from the center to any point on the circle is of length 1. So what would this coordinate be right over there, right where it intersects along the x-axis? Well, it would be x would be 1, y would be 0. What would this coordinate be up here? Well, we've gone 1 above the origin, but we haven't moved to the left or the right, so our x value is 0, our y value is 1. What about back here? Well, here our x value is -1. We've moved 1 to the left, and we haven't moved up or down, so our y value is 0. And what about down here? Well, we've gone a unit down, or 1 below the origin, but we haven't moved in the xy direction, so our x is 0, and our y is -1. Now, with that out of the way, I'm going to draw an angle. And then the way I'm going to draw this angle, I'm going to define a convention for positive angles. I'm going to say a positive angle, well, the initial side of an angle, we're always going to do along the positive x-axis. So this is you can kind of do the starting side of the angle, the initial side of an angle. And then to draw an angle, a positive angle, the terminal side, we're going to move in a counterclockwise direction. So positive angle means we're going counterclockwise. Counterclockwise. So this is just the convention I'm going to use, and it's also the convention that is typically used. And so you can imagine a negative angle would move in a clockwise direction. So let me draw a positive angle. So a positive angle might look something like this. This is the initial side, and then from that I go in a counterclockwise direction until I measure out the angle, and this is the terminal side. This is a positive angle theta. And what I want to do is think about this point of intersection between the terminal side of this angle and my unit circle. And let's just say it has the coordinates a, comma, b. The x value where it intersects is a, the y value where it intersects is b. And the whole point of what I'm doing here is I'm going to see how this unit circle might be able to help us extend our traditional definitions of trig functions. And so what I want to do is I want to make this theta part of a right triangle. So to make it part of a right triangle, let me drop an altitude right over here, and let me make it clear that this is a 90-degree angle. So this theta is part of this right triangle. So let's see what we can figure out about the sides of this right triangle. So the first question I have to ask you is, what is the length of the hypotenuse? What is the length of the hypotenuse of this right triangle that I've just constructed? Well, this hypotenuse is just a radius of a unit circle. The unit circle has a radius of 1, so the hypotenuse has length 1. Now, what is the length of this blue side right over here? This blue side, you could do this as the opposite side to the angle. Well, this height is the exact same thing as the y coordinate of this point of intersection. So this height right over here is going to be equal to b. The y coordinate right over here is b. This height is equal to b. Now, exact same logic. What is the length of this base going to be? The base just of the right triangle. Well, this is going to be the x coordinate of this point of intersection. If you were to drop this down, this is the point x is equal to a, or this whole length between the origin and that is of length a. Now that we have set that up, what is the cosine? And what is the cosine? Use the same green. What is the cosine of my angle going to be in terms of a's and b's and any other numbers that might show up? Well, to think about that, we just need our SOHCAHTOA definition. That's the only one we have now. We are actually in the process of extending it. SOHCAHTOA definition of trig functions. And the cut part is what helps us with cosine. It tells us that the cosine of an angle is equal to the length of the adjacent side over the hypotenuse. So what's this going to be? The length of the adjacent side, for this angle, the adjacent side has length a, so it's going to be equal to a over what's the length of the hypotenuse? Well, that's just 1. So the cosine of theta is just equal to a. Let me write this down again. So the cosine of theta is just equal to a. It's equal to the x coordinate of where this terminal side of the angle intersected the unit circle. Now let's think about the sine of theta. Sine of theta. And I'm going to do it in, let me see, I'll do it in orange. So what's the sine of theta going to be? Well, we just have to look at the SO part of our SOHCAHTOA definition. It tells us that sine is opposite over hypotenuse. Well, the opposite side here has length b, and with the hypotenuse has length 1. So our sine of theta is equal to b. So an interesting thing, this coordinate, this point where our terminal side of our angle intersected the unit circle, that point AB, we can also view this as a is the same thing as cosine of theta, a is the same thing as cosine of theta, and b is the same thing as sine of theta. Well, that's interesting. That was just we used our SOHCAHTOA definition. Now, can we in some way use this to extend SOHCAHTOA? The SOHCAHTOA has a problem. It works out fine if our angle is greater than 0 degrees, if we're dealing with degrees, and if it's less than 90 degrees. We can always make it part of a right triangle. But SOHCAHTOA starts to break down as our angle is either 0 or maybe even becomes negative, or as our angle is 90 degrees or more. You can't have a right triangle with two 90-degree angles, and it starts to break down. Let me make this clear. So sure, this is a right triangle, so the angle is pretty large. I can make the angle even larger and still have a right triangle even larger, but I can never get quite to 90 degrees. At 90 degrees, it's not clear that I have a right triangle anymore. It all seems to break down. And especially the case what happens when I go beyond 90 degrees. So let's see if we can use what we set up here. Let's set up a new definition of our trig functions, which is really an extension of SOHCAHTOA, and it's consistent with SOHCAHTOA. Instead of defining cosine as, if I have a right triangle and saying, okay, it's the adjacent over the hypotenuse, sine is the opposite over the hypotenuse, tangent is opposite over adjacent, why don't I just say, for any angle, I can draw it in the unit circle using this convention that I just set up, and let's just say that the cosine of our angle is equal to the x coordinate where we intersect, is equal to the x coordinate where the terminal side of our angle intersects the unit circle, where angle, I'll write the terminal side of angle intersects the unit circle. And why don't we define sine of theta to be equal to the y coordinate where the terminal side of the angle intersects the unit circle. So essentially for any angle, this point is going to define cosine of theta and sine of theta. And so what would be the reasonable definition for tangent of theta? Well, tangent of theta, even with SOHCAHTOA, could be defined as sine of theta over cosine of theta, which in this case is just going to be the y coordinate where we intersect the unit circle over the x coordinate. In the next few videos, I'll show some examples where we use a unit circle definition to start evaluating some trig ratios. On the right-hand side, we have a bunch of expressions that are just ratios of different information given in these two diagrams. And over here on the left, we have the sine taken of angle mkj, cosine of angle mkj, and tangent of angle mkj. And angle mkj is this angle right here, same thing as theta. So these two angles have the same measure. We see that there. What we want to do is figure out which of these expressions are equivalent to which of these expressions right here. And so I encourage you to pause pause the video and try to work this through on your own. Assuming you've had a go at it, so let's try to work this out. When you look at this diagram, it looks like the intention here on the left is this evokes the unit circle definition of trig functions. This is a unit circle right over here, and this evokes kind of the SOHCAHTOA definition because it's just kind of a plain vanilla right triangle. So just to remind ourselves, the SOHCAHTOA feeling it might be useful. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we can refer to this, and we can also refer to remind ourselves of the unit circle definition of trig functions. That the cosine of an angle is the x coordinate, and the sine of where this ray is the circle, and the sine of this angle is going to be the y coordinate. What we'll see through this video is that actually the unit circle definition is just an extension of SOHCAHTOA. So let's look first at x over y. So we have x is the x coordinate, it's also the length of this side over here. Relative to this angle, theta, that is the adjacent side. So x is equal to the adjacent side. What is y? Well, we say the unit circle, y is the length of the radius, which for this right triangle is also the hypotenuse. So we apply the SOHCAHTOA definition. X over 1 is adjacent over hypotenuse. Adjacent over hypotenuse. Adjacent over hypotenuse, that's cosine. So that's going to be, this is equal to cosine of theta. But theta is the same thing as angle MKJ. They have the same measure. So cosine of angle MKJ is equal to cosine of theta, which is equal to x over 1. Now let's move over to y over 1. Well, y is going to be the length of this side, right over here. Y is going to be this length relative to angle theta. That is the opposite side. That is the opposite side. Now, which trig function is opposite over hypotenuse? Opposite over hypotenuse, that's sine of theta. Sine of theta. So sine of angle MKJ is the same thing as sine of theta. We see the same measure. And now we see that's the same thing as y over 1. Now for both of these, I use the SOHCAHTOA definition. We could also use the unit circle definition. X over 1, that's the same thing. That's the same thing as x. The unit circle definition says, well, this x, the x coordinate of where this, the terminal side of this angle, this ray right over here, intersecting the circle, that by definition, by the unit circle definition, is the cosine of this angle. If x is equal to cosine of this angle. And the unit circle definition, the y coordinate is equal to the sine of this angle. We could have written this as x comma y divided by cosine theta sine. Now we have x over y. We have adjacent over opposite. This is equal to adjacent over opposite. Tangent is opposite over adjacent, not adjacent over opposite. This is reciprocal. This right here. We had to do 1 over here. And we later learned about that. It's not one of our choices, so we can figure this one out. Then we have y over x. Well, this is y is opposite. X is adjacent over theta. So this is adjacent of theta. This is one reciprocal, not the choices. Now k over j. Now this is opposite over adjacent, opposite over adjacent. That is equal to theta or k. J is equal to a over j. Now we have m over j. M over j. Hypotenuse over adjacent side. Hypotenuse over adjacent. Well, if it was adjacent over hypotenuse, we did cosine. This is the reciprocal of that. This is actually 1 over the cosine of theta, not one of my choices. This is here, so I'm just going to there. Then we have reciprocal j over m. That's adjacent over hypotenuse. Adjacent over hypotenuse is cosine. And then one last one, k over m. That's opposite over hypotenuse. Opposite over hypotenuse. That's going to be sine of theta. So this right over here is equal to sine of theta, which is the same thing as sine of angle MKJ, which is the same thing as all of these expressions. So this is equal to k over m. And we are done. ACB is going to be 2 pi minus 2 pi over 3. I'm going all the way around, but then I'm subtracting out this part right over here. Now what's 2 pi minus 2 pi over 3? Let's see, I can find a common denominator. Instead of writing it as 2 pi, I can write that as 6 pi over 3. So let me do that. It's going to be 6 pi over 3 minus 2 pi over 3. Well, that's going to be 4 pi over 3. 4 pi over 3. And the symbol right over here is 4 pi over 3. 4 pi over 3 radians. 2 pi minus 2 pi over 3. I'm going all the way around, but then I'm subtracting out this part right over here. What's 2 pi minus 2 pi over 3? Let's see, I can find a common denominator. Instead of writing it as 2 pi, I can write that as 6 pi over 3. So let me do that. It's going to be 6 pi over 3 minus 2 pi over 3. So that's going to be 4 pi. This angle right over here is 4 pi over 3. 4 pi radians. Now, what fraction is that? We're going to go all the way around the circle. Well, again, the circle angle is 4 pi over 3. If we go all the way around the circle, that's 2 pi. So this is the fraction of the entire circle that this arc represents. And so let's just multiply that times the entire circumference. Times 3 pi. Try to simplify that. Let's see, pi divided by pi takes 3 multiplied times the numerator. Go all the way around the circle, that's 2 pi. So this is the fraction of the entire circle that this arc represents. And so let's just multiply that times the entire circumference. Times 3 pi. Let's try to simplify. Let's see, we have pi divided by pi is equal to we take this 3 multiplied times the numerator, this 3 that cancels that 3. We're going to left with 4 pi over 2. 4 pi divided by 2 is equal to 2 pi. So that's the length. That's the length. work through this. And if all of this seems really unfamiliar, I encourage you to review degrees, radians, or furnace denominators on contact. But also we have some familiarity with it. So first of all, they're telling us that the measure of angle AOB is 5 pi over 6 radians. So AOB, we're talking about this angle right over here, is 5 pi over 6 radians. We know that the radius of the circle is, the radius of the circle is 6. You know, the distance right over here is 6. We also know that the distance right over here is also 6. That is equal to 6. We want to know what the y coordinate is. The y coordinate of A, we can also figure out by figure out what is this distance right here that I'm drawing there, and this would be A right here. So let's figure out the distance. So you might already be familiar that in radians, pi radians go all the way around, and pi radians is halfway around. This angle over here is going to be halfway around the circle, pi minus 5 pi over 6. 5 pi. Now pi is right is 6 pi. So when you do this fraction, we're going to be left 6 pi over 6 minus 5 pi over 6 is going to be 5 over 6 radians. Now this might not be familiar to you. What is pi over 6 radians? We know that pi radians is equal to 1 radian. Divide that by 6. This is equal to 2 degrees. Are the bells starting to ring now? Well, you might recognize this as 30, 60, 90. Why do I know that's 60? Well, because if one side is 90 degrees and one angle is 90 degrees, that's 30 degrees. They all add up. This is a typical triangle you see a lot in your geometry. You know what I'm talking about. And we also know that the side of the opposite, 30 is 1/2 the radius. And that by itself lets us know what's going on, because this is 1/2 the radius of the graph. The radius is 6, so 1/2 times 6 is 2. And then that is the y coordinate. So when you do this subtraction, you are going to be left with 6 pi over 6 minus 5 pi over 6 is going to equal to pi over 6 radians. Now this term might not be familiar to you. What is pi over 6 radians? Well, you can think about converting that to degrees. You know that pi radians is equal to 180 degrees. So you divide that by 6. This is equivalent to 30 degrees. 180 degrees is our L starting to ring there. So you might recognize this as 30, 60, 90. Why did I know that? Well, because if one side is 90 degrees, one angle is 90 degrees, that's 30 degrees. So maybe this is a typical triangle you see a lot in the no matter. And we also know that in the side that is opposite, 30 degrees is 1/2 the radius. And that by itself lets us know what's going on, because this is 1/2 the radius of the graph. The radius is 1/2 times 6 is equal to 3. And we're done. That is the y coordinate. It is 3. Of a circle C is x plus 3 squared plus y minus 4 squared is equal to 49. What are its center hk and its radius r? So let's just remind ourselves what a circle is. You have some point, let's call that hk. The circle is a set of all points that are equidistant from that point. So let's take the set of all points that are, say, r away from hk. So let's say that this distance right over here, this distance right over here is r. And so we want all the set of points that are exactly r away. So all the points x comma y that are exactly r away. And so you can imagine you could rotate around and all of these points are going to be exactly r away. I'm going to try my best to draw at least a somewhat perfect looking circle. I won't be able to do a perfect job of it, but you get a sense. All of these are exactly r away, at least if I were to draw it properly. They are r away. So how do we find an equation in terms of r and hk and x and y that describes all these points? Well, we know how to find the distance between 2 points on the coordinate plane. In fact, it comes straight out of the Pythagorean theorem. If we were to draw a vertical line right over here that essentially is the change in the vertical axis between these 2 points. Up here we're at y, here we're k, so this distance is going to be y minus k. We can do the exact same thing on the horizontal axis. This x coordinate is x, while this x coordinate is h. So this is going to be x. This is going to be x minus h is this distance. And this is a right triangle because by definition we're saying, hey, this is a vertical, we're measuring vertical distance here, we're measuring horizontal distance here, so these two things are perpendicular. And so from the Pythagorean theorem, we know that this squared plus this squared must be equal to our distance squared. This is where the distance formula comes from. So we know that x minus h squared plus plus y minus k squared must be equal to r squared. This is the equation for the set. This describes any x and y that satisfies this equation will sit on this circle. Now with that out of the way, let's go answer their question. The equation of the circle is this thing. And this looks awfully close to what we just wrote. We just have to make sure that we don't get confused with the negatives. Remember, it has to be in the form x minus h, y minus k. So let's write it a little bit different. Instead of x plus 3 squared, we can write that as x minus negative 3 squared. And plus, what is already in the form, plus y minus 4 squared is equal to, instead of 49, we can just call that 7 squared. And so now it becomes pretty clear that our h is negative 3. I want to do that in red color. That our h is negative 3, and that our k is positive 4, and that our r is 7. So we can say h comma k is equal to negative 3 comma positive 4. Make sure you get the, you might say, hey, there's a negative 4 here. No, but look, it's minus k, minus 4, so k is 4. Likewise, it's minus h. You might say, hey, maybe h is a positive 3, but no, you're subtracting the h, so you say minus negative 3. And similarly, the radius is 7. We're asked to graph the circle, and they give us this somewhat crazy looking equation. And then we can graph it right over here. And to graph a circle, you have to know where its center is, and you have to know what its radius is. So let me see if I can change it. You have to know what its radius is. So what we need to do is put this in some form where we can pick out its center and its radius. So let me get my little scratch pad out and see if we can do that. So this is that same equation. And what I essentially want to do is I want to complete the square in terms of x and complete the square in terms of y to put it into a form that we can recognize. So first let's take all of the x terms. So you have x squared and 4x on the left hand side. So I can rewrite this as x squared plus 4x. I'm going to put some parentheses around here because I'm going to complete the square. And then I have my y terms. I'll circle those in. Well, red looks too much like purple. I'll circle those in blue. Y squared and negative 4y. So we have plus y squared minus 4y, and then we have a minus 17, and I'll just do that in a different color. So minus 17 is equal to 0. Now, what I want to do is make each of these purple expressions perfect squares. So how could I do that here? Well, this would be a perfect square if I took half of this 4 and I squared it. So if I made this plus 4, then this entire expression would be x plus 2 squared. And you can verify that if you like. If you need a review on completing a square, there's plenty of videos on Khan Academy on that. All we did is we took half of this coefficient, and then squared it to get 4. Half of 4 is 2, squared to get 4. And that comes straight out of the idea. If you take x plus 2 and squared, it's going to be x squared plus twice the product of 2 and x plus 2 squared. Now, we can't just willy-nilly add a 4 here. We had an equality before. Just adding a 4 wouldn't be equal anymore. So if we want to maintain the equality, we have to add 4 on the right-hand side as well. Now let's do the same thing for the y's. Half of this coefficient right over here is a negative 2. If we square negative 2, it becomes a positive 4. We can't just do that on the left-hand side. We have to do that on the right-hand side as well. Now, we have in blue becomes y minus 2 squared. And of course, we have the minus 17. But why don't we add 17 to both sides as well to get rid of this minus 17 here? So let's add 17 on the left and add 17 on the right. So on the left, we're just left with these two expressions. And on the right, we have 4 plus 4 plus 17. Well, that's 8 plus 17, which is equal to 25. Now, this is a form that we recognize. If you have the form x minus a squared plus y minus b squared is equal to r squared, we know that the center is at the point a comma b, essentially the point that makes both of these equal to 0, and that the radius is going to be r. So if we look over here, what is our a? We have to be careful here. Our a is 2, our a is negative 2. X minus negative 2 is equal to 2. So the x coordinate of our center is going to be negative 2, and the y coordinate of our center is going to be 2. Remember, we care about the x value that makes this 0 and the y value that makes this 0. So the center is negative 2, comma 2, and this is the radius squared. So the radius is equal to 5. Radius is equal to 5. So let's go back to the exercise and actually plot this. So it's negative 2, comma 2. So our center is negative 2, comma 2. So that's right over there. X is negative 2, y is positive 2, and the radius is 5. So see, this would be 1, 2, 3, 4, 5. So it's a little bit wider than this. My pen is having trouble. There you go. 1, 2, 3, 4, 5. Let's check our answer. We got it right. diameter. In fact, the center of a circle is always going to be the midpoint of the two endpoints of the center of a diameter. If the diameter was this right over here, if the diameter was this over here, then once again, the center of the circle is the midpoint of that point right there. So to answer this question, we have to find the midpoint of this point. To find the midpoint, we just find the average of the exponents. So this is going to be 8. The average of the exponents is plus 2.
so much for playing my game.